Are there any questions, firstly, about the homework for Tuesday? Okay. So what we're going to do today is we're going to start talking about stochastic models. Now, we touched on stochastic models a little bit when we were talking about genetics, but then all the genetics models that we looked at were for large population sizes. And all the models that we've been looking at population processes for very large populations so that you can ignore something that is called demographic stochasticity. So demographic stochasticity is a process whereby if you have a certain number of individuals in the population and each has a certain probability of dying, then the number that actually die, is going to be what's called a random variable. And it's going to vary according to some distribution. So for example, if you've got one individual and that individual has a 0.5 probability of dying in the next time interval, then at the end of the time interval, you'll either have 1 or 0. You won't have a half an individual. But if you've got a million individuals, then what we've been doing is we've been building what we call deterministic models where you say, okay, if you've got a million individuals and each individual has a probability of 0.5 of surviving, then we're going to turn that probability into a proportion, and then we'll say 500,000 survived. And we do that because there's a theorem in probability theory called the law of large numbers. Anybody heard of this? Anybody want to tell me what the law of large numbers says? Just in your own words. It says that the probability for large populations approaches the actual proportions. That means the variance you see will get smaller and smaller until the population is so large that the variance is essentially 0. So if you've got 100 individuals and half of them are expected to die, you may have 45 that die or 55 that die. But if you've got a million individuals, then you're not going to get 450,000 that die or 550,000, but it'll be 498,000 or something like that. So it'll get closer and closer to the actual proportion. So we're going to start out with the concept of what's called a Bernoulli variable. A Bernoulli variable is a variable that has a certain probability of occurring or not occurring. So the ones that you're most familiar with are flipping a coin, where each time you do this, you can either get heads or tails. And from a mathematical point of view, it's convenient to say you either get 0 or 1. And then you ask, after I've done this 100 times, what proportion of them will be heads and what proportion will be tails, or what proportion will be zeros and what proportion will be ones. And to find that out, you can keep adding. You can add 0, 0, 1, 1, 1, 0, 1, 0, as you get heads and tails. And then you can divide by what's called the number of trials. So each flip of a coin is a trial, and then you divide by the number of trials, and so you approach the probability. Now, in a fair coin, the probability is 0.5. But sometimes, if you go and you see people on the street playing games of chance, and they invite you in, the chances are that what you think is a fair probability is not going to be a fair probability. They're doing something. And it could be that something as simple as a loaded die or a coin that is more likely to come up heads than tails for whatever reason. Now, the other thing about Bernoulli variables is an independence of trials. So if I flip a head, then the assumption is that the next trial, heads or tails, was independent of the fact that I got heads. Now, most gamblers don't believe in independence of trials. Even some who say, well, I've been unlucky for long enough, so now the chances that I'm going to be lucky are higher than normal. Anybody who thinks that is soon going to lose all their money, and very often they do. So you've seen this sort of thing, and you've seen this sort of thing in the context of the binomial theorem. And so the binomial theorem tells you about the probability of getting sequences of events. So for example, if I do an experiment and I flip a coin twice, I can either get 2 heads, or in this case 2 tails, a tail and a head and a tail, a head and a head. And if the probability of getting a tail is p, then the probability of this event is p times p, because I'm assuming independence. And this is p times 1 minus p times p, and 1 minus p squared. So we saw this kind of logic when we were thinking about in genetics, and we were looking at the experiments that were done with flowers, and looking at the probability of getting different genotypes when you have 2 allele models. Now, this is the case where you have 2 outcomes, where you have where your sample space is looking at two events. So you've got a trial, and each time it's done once, and then you want to count it after it's done twice. But you could count it after you've had n flips of the coin. And so then you ask, okay, what is the probability after n flips? And so what you're going to do is you're going to generalize the binomial theorem. So the binomial expansion says that I've got a probability p of getting 0, and a probability of q equal to 1 minus p of getting a 1. And then if I expand this out, you get this binomial expansion. Now, if you have a Bernoulli experiment with n flips of the coin, then it's the same as taking this expansion to the power n. And if you go back to the binomial expansion for n trials, you'll get something that looks like this expression over here, but this is called the number of ways of choosing r zeros out of a possible n zeros. And that's given by this expression in terms of the factorial. So has everybody seen that? Anybody not seen that? Okay. So if you expand this out and you ask what this coefficient is, there's something called Pascal's triangle for generating these coefficients. Once you've generated these coefficients, then you still have to do this part of the calculation, which is taking p to the power n minus r and q to the power r, where ultimately you understand q as 1 minus p. And you can generalize this to situations where instead of having 2 types of things, you can have 3 types of things, or m types of things. So for example, imagine you've got an urn, and in this urn you have 10 balls, and 3 are red, and 3 are black, and 4 are white. Then you can ask, what's the probability of getting 3 white balls in a row? And this is with replacements. I take a ball out, look at its color, put it back in. Take a ball out, look at its color, put it back in. So the probability of getting 3 white balls in a row has to do with the fact that 3 of the balls out of the 10 are white. So the probability of getting a white ball at any event is 0.3. So it's going to be equal to 0.3 times 0.3 times 0.3 is what gives you this part of it. But then you have to look at what the whole sample space looks like. So these numbers, which are from combinatorics, the CNRs, in the case of the binomial, the weighting is 1 and 1. Sorry, the weighting is 1, 2, and 1. And the reason why it's 1, 2, and 1 is because if you're looking at the number of ways you can get a 0, 1, 0, and 1, 1, there are two different ways you can get it. There's only one way you can get 0, 0, one way in which you can get 1, 1, but there are two different ways in which you can get 0 and 1. So that's the number of combinations in which you can get 1, 0, and 1, 1. There are two of them out of the four possible things that can happen. And so if you do a cubic expansion, then you get the coefficients 1, 3, 3, 1, and a quartic expansion 1, 4, 6, 4, 1. And the way you generate this triangle is you start off with 1 and put 1 and 1 there, and then you always put 1s on the outside, and then to get this one you add 1 and 1 is 2, and here you get 1 and 1 is 3, sorry, 1 and 2 are 3, 1 and 2 are 3. Here you get 1 and 3 are 4, 3 and 3 are 6, 3 and 1 is 4, and 1 and 4 is 5, 4 and 6 are 10, and so on. You never have to worry about how to do this now because you've got calculators. And in what we're going to do, all you do is you call the binomial function, and when you call a binomial function, the binomial function has two parameters. So if you call the binomial function in Nova, you put over here how big your sample size is. Is it going to be 2? Is it going to be 3? Is it going to be 4? It's going to be n, and the other parameter is p. So for example, if n is 3, and then p is a third, then the probability of getting 0, 0, 0 is going to be 1 times, now 1 is going to be your c, and then your p is a third, and you're going to cube this, and then the probability of getting 2 zeros and a 1. So you can get this in three different ways. You can get 0, 0, 1, 0, 1, 0, 0, 1. So that's going to be 3 times p is a third, sorry. A third squared, 2 thirds, which is your cube to the power 1. So that's how you can do all these calculations. So I just want to make sure that you understand, you're not going to have to do calculations like this, but when you call the binomial theorem, these will be the probabilities that the different combinations come up. So let's say they're going to come up in the context of what we're doing. If individuals reproduce, and they can have a little size of either 0, 1, 2, or 3, and then you say, what's the expected number they're going to get? And if the expected number is 1.6 individuals, but a certain proportion of the time they'll get nothing, a certain proportion of the time they get 1, a certain proportion of the time they get 2, and a certain proportion of the time they get 3, then you want to know what those proportions are. So if I look at how many litters are of size 0, how many of size 1, how many of size 2, how many of size 3, then I use the binomial theorem. And it turns out that for the binomial theorem, the mean is equal to n times p. So if I say to you, you can have a litter size of 3, so you get anywhere from 0 to 3, and the average size is equal to 1.6, then I'll say, what is p? So that's the average size. So if the average size is 1.6, it means that n times p is equal to 1.6, and n is equal to 3, so p must be equal to 1.6 over 3. And if p is equal to 1.6 over 3, then how many times will I expect to get a litter size of 0? How many times 1, or what proportion of times, I should rather say. And so these calculations can all arise. But again, you're not going to have to do these calculations. They're going to be done in the computer. Now, in order to use things like the binomial function in the computer, you have to use random numbers. And so computers have random number generators, ways of generating random numbers. And typically in a computer, if you say random, and in this case with Nova or JavaScript, you just leave open brackets like that, this function in Nova and in JavaScript will give you a number between 0 and 1 to a certain number of decimal places. So depending on the software, will depend on how many decimal places it will deliver the number to you. Yeah. No, 0 is possible. Yeah, so it'll be 1.6 over 3 is the p to the power 4. That's the probability of getting zeros, all zeros. So if the litter size is 4 individuals, you can think of, in the nest there are these 4 boxes, and the females delivering babies into it. So some females will deliver nothing into any of the boxes, they don't have any. Some females will deliver 1 into one of the boxes. Now, there are 4 different ways she can deliver 1. So it's going to be 4 times the probability of getting one of these. And the probability of this is calculated in terms of p. N is the number of boxes. And the actual number of individuals that any female can expect to have is n times p. But any female will either have 0, 1, 2, 3, or 4 in the litter size. So what proportion of the time will she have 0, what proportion 1, what proportion 2, what proportion 3, or 4? Yeah. You can only take averages across a population. So you've got 1,000 females. Excuse me at the back. Please put your phone away. Thank you. You can only, if you have 1,000 females, some females will have 0, some will 1, some 2, some 3, some 4. And if I look at all the females and I look at all their litter sizes and I average it, let's say it comes to 1.6. But I know some of them are not having any. Some are having 1, some are 2. So nobody's having 1.6. That's just your average. So then I'm going to say, if the average litter size is 1.6, but the maximum litter size is 4, and if the distribution of litter sizes is binomial, then this holds. So that means the only possible space for this is 0, 0, 0, 3 zeros and a 1, but the 3 zeros and a 1 you can get in 4 different ways. Or it's 2 zeros and 2 1s, which you can get in, if you look at Pascal's triangle, you can get in 6 different ways. Or 3 1s and a 0, which you can get in 4 different ways. But then there's the probability that you get that. So that's where the P's and Q's come in that calculation. Okay? Is there a question at the back? Okay. Yeah. Yeah, the litter size is the range. So you can't have 100. There are some distributions, like a Poisson distribution, where it might be open-ended, it's not bounded. But for a binomial distribution, there are 2 parameters. There's the maximum size, and then there's the probability that in each of the boxes, so there's a number of boxes, and then the probability of a 0 or 1 in each of the boxes. So the assumption that it's going to be binomial is not necessarily correct. In other words, it may be that 4 is the maximum size, but almost every female has 2, and very occasionally a female might have 3 or 4, but that's very rare, and that wouldn't be binomial. So to say it's binomial is to kind of think about a female as having 4 boxes in a nest, or 4 cavities in the womb. So if you have a look at the physiology of some mammals, that physiology actually determines how the maximum size of a litter. It can't just be completely open-ended. I'm just going to switch down this because I think my computer can. Okay, so does everybody understand this? Yeah. Right. So in other words, well, so you know, when a woman has quintuplets, it's usually, I don't know of any natural situation where women have quintuplets. It's been done for fertility treatment. I think you naturally get triplets very occasionally, but I don't think that would follow a binomial because it's so rare. But in the models that we're going to build, we're going to just make a simplifying assumption, just to demonstrate the methods. When you have, I mean, what would happen is, in reality, in the real world, if you were a biologist, you would say, okay, I'm going to have a look at litter sizes. And let's say there's some organism that has anywhere from 0, 1, 2, and 3. Now, it may turn out that most often that it's often 1 and it's very often 2, but it's not that very often 0 or 3. If you had a look at the mean of this distribution and then you did a binomial for that mean, it may turn out that in order to get the same mean for a binomial that has 3, it would look more like this. And so, let's see, it would look more like this. So this would be more than the binomial predicts. This would be less than the binomial predicts. So this wouldn't be a good fit to the binomial. So then you'd have to try some other distribution that gives you a better fit. But there may be no simple distribution that gives you a better fit, and then you can use these data directly and in your model. So, but we don't have any data, so we're going to assume in our models that when we build a model of what's going on in terms of births and deaths, that it's a binomial. In terms of deaths, we're just going to assume that it's either a 0 or a 1 that occurs with a certain probability. So if a third of the individuals are dying, then you say we're going to have a binomial of 0, 1 with p equal to a third in terms of a third of the time I'll get zeros and 1 minus p, 2/3 of the time I'll get 1s. And so it's very simple if it's just 0 and 1, which is the case with death, because you've got an individual, and then at the next time period, the individual can be alive or dead. If you have births, then if we say an individual can have 0 or 1 with probability, and the average size is 0.8, then you're going to have 1 with probability 0.8 and 0 with probability 0.2. But we know that with births, it's a little more complicated. It's not only 0 or 1, but it could be 0, 1, 2, 3, or 4, or 5, or up to n, where n is the maximum size for any litter. Okay? So once we've done this, we come to say, okay, we're going to use computers to generate models that have this, what's called demographic stochasticity. Stochasticity means that there's the element of chance. And demography means that this chance is related purely to birth and death processes. So if you've got a very large number of individuals on the order of millions, then you can just do a deterministic model, and you don't have to worry about this variation, because the variation is very small compared to the mean. And the mean, and your model is not that exact because the parameters are not that well estimated, so that variation is within the error of the estimates of p. But if you've got a small number of individuals, particularly if you're a conservation biologist. Now, for example, if you're a conservation biologist, and there are 10 individuals in the population, and you want to say, what is the probability that they'll all be dead in 5 years? Okay, that's gone extinct. So you can imagine with these 10 individuals,